Sputnik 1.
Sputnik 1 was the first artificial Earth satellite. It was a 58 cm diameter polished metal sphere, with 4 external radio antennas to broadcast radio pulses. The Soviet Union launched it into an elliptical low Earth orbit on October 4, 1957. It was visible all around the Earth and its radio pulses were detectable. The surprise success precipitated the American Sputnik crisis and triggered the space race, a part of the larger Cold War. The launch ushered in new political, military, technological, and scientific developments. Sputnik itself provided scientists with valuable information. The density of the upper atmosphere could be deduced from its drag on the orbit, and the propagation of its radio signals gave information about the ionosphere. Sputnik 1 was launched during the International Geophysical Year from Site No. 1/5, at the 5th Chirotam Range, in Kazakh SSR, now at the Baikonur Cosmodrome. The satellite traveled at about 29,000 km per hour, 18,000 miles per hour, 8,100 meters per second, taking 96.2 minutes to complete each orbit. It transmitted on 20.005 and 40.002 MHz, which were monitored by amateur radio operators throughout the world. The signals continued for 22 days until the transmitter batteries ran out on October 26, 1957. Sputnik 1 burned up on January 4, 1958, as it fell from orbit upon re-entering Earth's atmosphere, after traveling about 70 million km, 43.5 million miles, and spending 3 months in orbit.
Before the launch. Satellite construction project.
The history of the Sputnik 1 project dates back to December 17, 1954, when Sergei Korolev addressed Dmitry Ustinov, the Minister of Defense Industries, proposing the development of an Earth-orbiting, artificial, satellite, forwarding a report by Mikhail Tikhonravov with an overview of similar projects abroad. Tikhonravov emphasized that an artificial satellite is an inevitable stage in the development of rocket equipment in 1951, after which interplanetary communication would become possible. On July 29, 1955, the U.S. President Dwight D. Eisenhower announced, through his press secretary, that the United States would launch an artificial satellite during the International Geophysical Year, IGY. A week later, on August 8, the Presidium of the Central Committee of the CPSU approved the idea of creating an artificial satellite. On August 30, Vasily Ryabikov, the head of the State Commission on A-7 rocket test launches, held a meeting where Korolev presented calculation data for a spaceflight trajectory to the Moon. They decided to develop a 3-stage version of the A-7 rocket for satellite launches. On January 30, 1956, the Council of Ministers approved practical work on an artificial Earth-orbiting satellite. This satellite, named Object D, was planned to be completed in 1957-58. It would have a mass of 1,000 to 1,400 kilograms, 2,200 to 3,100 pounds, and would carry 200 to 300 kilograms, 440 to 660 pounds, of scientific instruments. The first test launch of Object D was scheduled for 1957. According to that decision, work on the satellite was to be divided between institutions as follows. USSR Academy of Sciences was responsible for the general scientific leadership and research instrument supply. Ministry of Defense Industry and its main executor OKB-1 were assigned the task of creating the satellite as a special carrier for scientific research instruments. Ministry of Radio-Technical Industry would develop the control system, radio-technical instruments and the telemetry system. Ministry of Shipbuilding Industry would develop gyroscope devices. Ministry of Machine Building would develop ground launching, refueling and transportation means. Ministry of Defense was responsible for conducting launches. Thanks to Dmitry Sergeyevich Mordasov, the main engineer, by July 1956 the draft was completed and the scientific tasks to be carried out by the satellite were defined. It included measuring the density of the atmosphere, its ion composition, corpuscular solar radiation, magnetic fields, cosmic rays, etc. data valuable in creating future satellites was also to be collected. A ground observational complex was to be developed that would collect information transmitted by the satellite, observe the satellite's orbit, and transmit commands to the satellite. Such a complex should include up to 15 measurement stations. Because of the limited time frame, they should have means designed for rocket R7 observations. Observations were planned for only 7 to 10 days and orbit calculations were expected to be not quite accurate. Unfortunately, the complexity of the ambitious design and problems in following exact specifications meant that some parts of Object D, when delivered for assembly, simply did not fit with the others, causing very costly delays. By the end of 1956 it became clear that plans for Object D were not to be fulfilled in time because of difficulties creating scientific instruments and the low specific impulse produced by the completed R7 engines, 304 seconds instead of the planned 309 to 310 seconds. Consequently, the government rescheduled the launch for April 1958. Object D would later fly as Sputnik 3. Fearing the U.S. would launch a satellite before the USSR, OKB-1 suggested the creation and launch of a satellite in April-May 1957, before the IGY began in July 1957. The new satellite would be simple, light, 100 kilograms or 220 pounds, and easy to construct, foregoing the complex, heavy scientific equipment in favor of a simple radio transmitter. On February 15, 1957 the Council of Ministers of the USSR approved this, providing for launching the simplest version satellite, designated Object PS. This version also facilitated the satellite to be tracked visually by Earth-based observers while in orbit, and transmit tracking signals to ground-based receiving stations. Launch of two satellites PS-1 and PS-2 with two R-7 rockets, 8K-71, was allowed, but only after one or two successful R-7 test launches.
Launch vehicle preparation and launch site selection.
The two-stage R-7 Semyoka was initially designed as an ICBM by OKB-1. The decision to build it was made by the CPSU Central Committee and the Council of Ministers of the USSR on May 20, 1954. The R-7 was also known by its GRAU, later GUAVO, designation 8K-71. Due to Soviet secrecy at the time, the R-7 was known to Western sources as the T-3 or M-104, and Type AA Special Reconnaissance Commission selected Chirotam as a place for the construction of a rocket proving ground, the 5th Chirotam range, usually referred to as NIIP-5, or GIK-5 in the post-Soviet time. The selection was approved on February 12, 1955 by the Council of Ministers of the USSR, but the site would not be completed until 1958. Actual work on the construction of the site began on July 20 by military building units. On June 14, 1956, Sergei Korolev decided to adapt the R-7 rocket to the Object D, that would later be replaced by the much lighter Object PS. The first launch of an R-7 rocket, 8K-71 No. 5L, occurred on May 15, 1957. The flight was controlled until the 98th second, but a fire in a strap-on rocket led to an unintended crash 400 kilometers from the site. 3 attempts to launch the second rocket, 8K-71 No. 6, were made on 10 to 11 June, which failed because of a mistake made during the rocket's assembly. The unsuccessful launch of the third R-7 rocket, 8K-71 No. 7, took place on July 12. During the flight the rocket began to rotate about its longitudinal axis and its engines were automatically turned off. The packet of stages was destroyed 32.9 seconds into the flight. The stages fell 7 kilometers, 4.3 miles, from the site and exploded. The launch of the fourth rocket, 8K-71 No. 8, on August 21 at 15:25 Moscow time, was successful. Its head part separated, reached a defined region, entered the atmosphere, and was destroyed at a height of 10 kilometers, 6.2 miles, because of thermodynamic overload after traveling 6,000 kilometers. On August 27 TASS in the USSR issued a statement on the launch of a long-distance multistage ICBM. The launch of the fifth R-7 rocket, 8K-71 No. 9, on September 7 was also successful, but the head part was also destroyed in the atmosphere, and hence needed a long redesign to completely fit its military purpose. The rocket, however, was already suitable for scientific satellite launches, and following the successful launches, Korolev was able to convince the State Commission to allow the use of the next R-7 to launch a hastily designed and built satellite, allowing the delay in the rocket's military exploitation to launch the PS-1 and PS-2 satellites. On September 22 a modified R-7 rocket, named Sputnik and indexed as 8K-71PS, arrived at the proving ground and preparations for the launch of PS-1 began. As the R-7 was designed to carry the much heavier Object D, its adaptation to PS-1 reduced its initial mass from 280 to 272.83 short tons, 254 to 248 metric tons, and its mass at launch was 267 short tons, 242 metric tons. Its length with PS-1 was 29.167 meters, 95 feet 8.3 in, and the thrust was 3.90 mn, 880,000 pound forces.
Observation Complex.
The measurement complex at the proving ground for monitoring the launch vehicle from its launch was completed prior to the first R-7 rocket test launches in December 1956. It consisted of 6 static stations, IP-1 through IP-6, with IP-1 situated at a distance of 1 kilometer, 0.62 miles, from the launch pad. The main monitoring devices of these stations were telemetry and trajectory measurement stations, TRAL, developed by OKB-MEI. They received and monitored data from the TRAL system transponders mounted on the R-7 rocket. An onboard system that provided precise telemetric data about Sputnik 1's launch vehicle. The data was useful even after the satellite's separation from the second stage of the rocket. Sputnik 1's location was calculated from the data on the second stage's location, which followed Sputnik 1 at a known distance, using nomograms developed by P.E. Eliasberg. An additional observation complex, established to track the satellite after its separation from the rocket, was completed by a group led by Colonel U.A. Mozharin in accordance with the General Staff Directive of May 8, 1957. It was called the Command Measurement Complex and consisted of the Coordination Center and NII-4 by the Ministry of Defense of the USSR, at Bolshevo, and 7 ground tracking stations, situated along the line of the satellite's ground track. They were, NIP-1, at Chirotam Station, Kazakh SSR, situated not far from IP-1, NIP-2, at Makat Station, Garayev Oblast, NIP-3, at Saryshagan Station, Zhitskazgan Oblast, NIP-4, at Yeniseisk, NIP-5, at Village Iskup, Krasnoyarsk Krai, NIP-6, at Yelitsevo, and NIP-7, at Klyuchi. The complex had a communication channel with a launch pad. Stations were equipped with radar, optical instruments, and communication systems. PS-1 was not designed to be controlled, it could only be observed. Data from stations were transmitted by telegraphs into NII-4 where ballistics specialists calculated orbital parameters. The complex became an early prototype of the Soviet Mission Control Center. In the West, the satellite was tracked by amateur radio operators, and the booster rocket was located and tracked by a 36 MCS receiver on the Loveal telescope at the Jodrell Bank Observatory. The Newbrook Observatory was the first facility in North America to photograph Sputnik 1.
Design.
The chief constructor of Sputnik 1 at OKB-1 was M.S. Khomyakov. The satellite was a 585 mm, 23.0 in, diameter sphere, assembled from 2 hemispheres which were hermetically sealed using O-rings and connected using 36 bolts, and had a mass of 83.6 kilograms, 184 pounds. The hemispheres were 2 mm thick, and were covered with a highly polished 1 mm thick heat shield made of aluminium magnesium titanium AMG6T alloy. AMG is an abbreviation for aluminium magnesium, and T stands for titanium. The alloy contains 6% of magnesium and 0.2% of titanium. The satellite carried 2 pairs of antennas designed by the antenna laboratory of OKB-1 led by M.V. Kryushkin. Each antenna was made up of 2 whip-like parts, 2.4 and 2.9 meters, 7.9 and 9.5 feet, in length, and had an almost spherical radiation pattern, so that the satellite beeps were transmitted with equal power in all directions, making reception of the transmitted signal independent of the satellite's rotation. The whip-like pairs of antennas resembled 4 long whiskers pointing to one side, at equal 35-degree angles with the longitudinal axis of the satellite. The power supply, with a mass of 51 kilograms, 112 pounds, was in the shape of an octagonal nut with a radio transmitter in its hole. It consisted of 3 silver-zinc batteries, developed at the All-Union Research Institute of Current Sources, VNIIT, under the leadership of N.S. Lidorenko. 2 of them powered the radio transmitter and 1 powered the temperature regulation system. They were expected to fade out in 2 weeks, but ended up working for 22 days. The power supply was turned on automatically at the moment of the satellite's separation from the second stage of the rocket. The satellite had a 1-watt, 3.5 kilograms, 7.7 pounds, radio transmitting unit inside, developed by V.I. Lapo from NII 885, that worked on 2 frequencies, 20.005 and 40.002 MHz. Signals on the first frequency were transmitted in 0.3 seconds pulses, under normal temperature and pressure conditions on board, with pauses of the same duration filled by pulses on the second frequency. Analysis of the radio signals was used to gather information about the electron density of the ionosphere. Temperature and pressure were encoded in the duration of radio beeps, which additionally indicated that the satellite had not been punctured by a meteorite. The temperature regulation system contained a fan, a dual thermal switch, and a control thermal switch. If the temperature inside the satellite exceeded 36 DEGC, 97 DEGF, the fan was turned on, and when it fell below 20 DEGC, 68 DEGF, the fan was turned off by the dual thermal switch. If the temperature exceeded 50 DEGC, 122 DEGF, or fell below 0 DEGC, 32 DEGF, another control thermal switch was activated, changing the duration of the radio signal pulses. Sputnik 1 was filled with dry nitrogen, pressurized to 1.3 atmospheres. For the pressure control, the satellite had a barometric switch, activated when the pressure inside the satellite fell below 130 kilopascals, changing the duration of radio signal impulse. While attached to the rocket, Sputnik 1 was protected by a cone-shaped payload fairing, with a height of 80 centimeters, 31.5 in, and an aperture of 48 degrees. The fairing separated from both Sputnik 1 and the rocket at the same time when the satellite was ejected. Tests of the satellite were conducted at OKB-1 under the leadership of O.G. Ivanovsky.
Launch and mission.
The control system of the Sputnik rocket was tuned to provide an orbit with the following parameters: perigee height, 223 kilometers, 139 miles, apogee height, 1,450 kilometers, 900 miles, orbital period, 101.5 minutes. A rocket trajectory with these parameters was calculated earlier by Georgy Grichko, after completing the calculations over several nights on the USSR Academy of Sciences mainframe computer. The Sputnik rocket was launched on October 4, 1957 at 19:28 and 34 seconds UTC, October 5 at the launch site, from Site Number 1 at NIIP-5. Processing of the information obtained from the TRAL system showed that the Psi boosters separated 116.38 seconds into the flight, and the second stage engine was shut down 294.6 seconds into the flight. At this moment the second stage with PS-1 attached had a height of 223 kilometers, 139 miles, above Earth's surface, a velocity of 7,780 meters per second, 25,500 feet per second, and velocity vector inclination to the local horizon was 0 degrees 24 minutes. This resulted in an initial orbit with a perigee of 223 kilometers, 139 miles, an apogee of 950 kilometers, 590 miles, 65.1 degrees of inclination and a period of 96.2 minutes. After 3.14 seconds, PS1 separated from the second stage, and at the same moment at the small Finnish house of IP1 station, Junior Engineer Lieutenant V.G. Borisov heard the beep 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 signals from the radio receiver R250, CRU, R250, Radio Priamnik. Reception lasted for 2 minutes, while PS1 was above the horizon. There were many people in the house, both military and civil, and they were probably the first to celebrate the event. After 325.44 seconds, a corner reflector on the second stage was opened, that also allowed measurement of its orbit parameters, like the working TREL system did. The designers, engineers and technicians who developed the rocket and satellite watched the launch from the range. After the launch, they ran to the mobile radio station to listen to signals from the satellite. They waited about 90 minutes to ensure that the satellite had made one orbit and was transmitting, before Kirillaev called Soviet Premier Nikita Khrushchev. The downlink telemetry included data on temperatures inside and on the surface of the sphere. On the first orbit, the Telegraph Agency of the Soviet Union, TASS, transmitted, as result of great, intense work of scientific institutes and design bureaus, the first artificial Earth satellite has been built. The Sputnik 1 rocket booster, second stage of the rocket, also reached Earth orbit and was visible from the ground at night as a first-magnitude object following the satellite. Kirillaev had intentionally requested reflective panels placed on the booster in order to make it so visible. The satellite itself, a small but highly polished sphere, was barely visible at sixth magnitude, and thus more difficult to follow optically. Ahead of Sputnik 1 flew the third object, the payload-faring, 80 centimeters, 31 inches, long cone, that is a little bit bigger than the satellite. Sputnik 1 remained in orbit until January 4, 1958, when it decayed and re-entered the atmosphere, having completed 1,440 orbits of the Earth.
Reaction.
Teams of visual observers at 150 stations in the United States and other countries were alerted during the night to watch for the Soviet sphere at dawn and during the evening twilight. They had been organized in Project Moonwatch to sight the satellite through binoculars or telescopes as it passed overhead. The USSR asked radio amateurs and commercial stations to record the sound of the satellite on magnetic tape. News reports at the time pointed out that anyone possessing a shortwave receiver can hear the new Russian Earth satellite as it hurtles over his area of the globe. Directions, provided by the American Radio Relay League, were to tune in 20 megacycles sharply, by the time signals, given on that frequency. Then tune to slightly higher frequencies. The beep, beep sound of the satellite can be heard each time it rounds the globe. The first recording of Sputnik 1's signal was made by RCA engineers near Riverhead, Long Island. They then drove the tape recording into Manhattan for broadcast to the public over NBC radio. However, as Sputnik rose higher over the East Coast, its signal was picked up by ham station W2AE, the ham radio station of Columbia University. Students working in the university's FM station, WKCR, made a tape of this, and were the first to rebroadcast the Sputnik 1 signal to the American public, or such of it as could receive the FM station. At first the Soviet Union agreed to use equipment compatible with that of the United States, but later announced the lower frequencies. The White House declined to comment on military aspects of the launch, but said it did not come as a surprise. On October 5 the Naval Research Laboratory announced it had recorded 4 crossings of Sputnik 1 over the United States. The USAF Cambridge Research Center collaborated with Bendix Friars, Westinghouse Broadcasting Company, Smithsonian Astrophysical Observatory, and MIT, to obtain a motion picture of the rocket body of Sputnik 1 crossing the pre-dawn sky of Baltimore, broadcast on October 12 by WBZ-TV in Boston. U.S. President Eisenhower obtained photographs of the Soviet facilities from Lockheed U-2 flights conducted since 1956. The USSR's launch of Sputnik spurred the United States to create the Advanced Research Projects Agency, ARPA or DARPA, in February 1958 to regain a technological lead. In Britain, the media and population initially reacted with a mixture of fear for the future, but also amazement about humankind's progress. Many newspapers and magazines heralded the arrival of the space age. However, when the Soviet Union launched a second craft containing the dog Laika, the media narrative returned to one of anti-communism and many people sent protests to the Russian embassy and the RSPCA.
Propaganda.
Sputnik 1 was not immediately used by Soviet propaganda. The Soviets were focused on their own scientific goals and determination to win the space race and kept quiet about their earlier accomplishments, fearing that it would lead to secrets being revealed and possible failures being exploited by the enemy. When the Soviets began using Sputnik in their propaganda, they emphasized pride in the achievement of Soviet technology, arguing that it demonstrated the Soviets' superiority over the West. People were encouraged to listen to Sputnik's signals on the radio and to look out for Sputnik in the night sky. Reportedly, the body of the spacecraft had been highly polished in order to make it visible, via telescope, from the surface of the planet. However, what watchers actually saw was a stage of the carrier rocket. Shortly after the launch of PS-1, Khrushchev pressed Korolev to launch another satellite in time for the 40th anniversary of the October Revolution on November 7, 1957. The value of Sputnik to Soviet propaganda was especially evident in the response of the American public, as it surprised the American public, resulting in a wave of near hysteria. Not only did Sputnik shatter the perception of the United States as the technological superpower and the Soviet Union as a backward country, as their own Project Vanguard was caught off guard by the Soviets' early launch. The satellite's launch also evoked fears that with the Soviets protruding into space would put the U.S. territory at their mercy and force the Americans to take up a more offensive stance in the emerging space race, resulting in an emphasis on science and technological research and reforms in many areas from the military to education systems. The federal government began pouring unmatched amounts of money into science education, engineering and mathematics at all levels of education. An advanced research group was assembled for military purposes. These research groups developed weapons such as ICBMs and missile defense systems, as well as spy satellites for the U.S. About 4 months after the launch of Sputnik, after several failed attempts, the U.S. successfully launched a satellite, Explorer I, on January 31, 1958. The space race culminated in the U.S. moon landing in 1969.
Replicas.
A model of Sputnik 1 was given to the United Nations and now decorates the entry hall of its headquarters in New York City. Other replicas are on display at the Smithsonian's National Air and Space Museum in Washington, D.C. At the Kansas Cosmosphere and Space Center in Hutchinson, Kansas. At the Science Museum, London. At the World Museum in Liverpool. And hanging in the Noble Planetarium at the Fort Worth Museum of Science and History in Fort Worth, Texas. 3 1/3 scale student-built replicas of Sputnik 1 were deployed from the Mir space station between 1997 and 1999. The first, named Sputnik 40 to commemorate the 40th anniversary of the launch of Sputnik 1, was deployed in November 1997. Sputnik 41 was launched a year later, and Sputnik 99 was deployed in February 1999. A fourth replica was launched but never deployed, and was destroyed when Mir was deorbited. A full-scale model of Sputnik 1 is on display at the California Science Center in Los Angeles, California.
Impact.
Initially, U.S. President Eisenhower was not surprised by Sputnik. He had been forewarned of the R-7's capabilities by information derived from U-2 spy plane overflight photos as well as signals and telemetry intercepts. The Eisenhower administration's first response was low-key and almost dismissive. Eisenhower was even pleased that the USSR, not the USA, would be the first to test the waters of the still uncertain legal status of orbital satellite overflights. Eisenhower had suffered the Soviet protests and shoot-downs of Project Gentrix, Moby Dick, balloons and was concerned about the probability of a U-2 being shot down. In order to set a precedent for freedom of space before the launch of America's secret WS-117L spy satellites, the USA had launched Project Vanguard as its own civilian satellite entry for the International Geophysical Year. Eisenhower greatly underestimated the reaction of the American public, which was shocked by the launch of Sputnik 1 and by the televised failure of the Vanguard Test Vehicle 3 launch attempt. The sense of fear was inflamed by Democratic politicians and professional Cold Warriors which portrayed the United States as woefully behind. One of the many books which suddenly appeared for the lay audience noted 7 points of impact upon the nation. Those points of impact were, Western leadership, Western strategy and tactics, missile production, applied research, basic research, education, and democratic culture. The USA soon had a number of successful satellites, including Explorer 1, Project SCORE, and Courier 1B. However, public reaction to the Sputnik crisis led to the creation of the Advanced Research Projects Agency, renamed the Defense Advanced Research Projects Agency or DARPA in 1972, NASA, and an increase in U.S. government spending on scientific research and education. Not only did the launch of Sputnik spur America to action in the space race, it also led directly to the creation of NASA. Through the Space Act Bill, Sputnik also contributed directly to advancement in science and technology. This came about when President Eisenhower enacted a bill called the National Defense Education Act. This bill encouraged students to go to college and study math and science. The students' tuition fees would be paid for. This led to a new emphasis on science and technology in American schools. Sputnik also created building blocks which probably led to the general establishment of the way science is conducted in the United States today. One consequence of the Sputnik shock was the perception of a missile gap. This was to become a dominant issue in the 1960 presidential campaign. One irony of the Sputnik event was the initially low-key response of the Soviet Union. The Communist Party newspaper Pravda only printed a few paragraphs about Sputnik 1 on October 4. In the days following the world's startled response, the Soviets started celebrating their great accomplishment. Sputnik also inspired a generation of engineers and scientists. Harrison Storms, the North American designer who was responsible for the X-15 rocket plane, and went on to head the effort to design the Apollo Command Service Module and Saturn V launch vehicle's second stage, was moved by the launch of Sputnik to think of space as being the next step for America. Astronauts Alan Shepard, who was the first American in space, and Deke Slayton later wrote of how the sight of Sputnik I passing overhead inspired them to their new careers. Homer Hickham's memoir Rocket Boys and the movie October Sky tell the story of how a coal miner's son, inspired by Sputnik, started building rockets in the mining town where he lived. The launch of Sputnik 1 inspired U.S. writer Herb Cohen to coin the term beatnik in an article about the Beat generation in the San Francisco Chronicle on April 2, 1958.
Backup units.
A Sputnik 1 backup unit is on display at the personal library of Jay Walker, an Internet entrepreneur. In 2003 a backup unit of Sputnik 1 called Model PS1 failed to sell on eBay. It was offered while still on display in a science institute near Kiev. It is estimated that between 4 and 20 models were made for testing and as replicas. What is thought to be a backup of Sputnik 1 now hangs at the Museum of Flight in Seattle, Washington. The craft was manufactured by the Soviet Academy of Sciences and has battery acid remnants on the inside walls of the spherical shell, as well as fittings for the various components, suggesting that it was more than
Sputnik 1.
Sputnik 1 was the first artificial Earth satellite. It was a 58 cm diameter polished metal sphere, with 4 external radio antennas to broadcast radio pulses. The Soviet Union launched it into an elliptical low Earth orbit on October 4, 1957. It was visible all around the Earth and its radio pulses were detectable. The surprise success precipitated the American Sputnik crisis and triggered the space race, a part of the larger Cold War. The launch ushered in new political, military, technological, and scientific developments. Sputnik itself provided scientists with valuable information. The density of the upper atmosphere could be deduced from its drag on the orbit, and the propagation of its radio signals gave information about the ionosphere. Sputnik 1 was launched during the International Geophysical Year from Site No. 1. Industry and its main executor OKB-1 were assigned the task of creating the satellite as a special carrier for scientific research instruments. Ministry of Radio-Technical Industry would develop the control system, radio-technical instruments and the telemetry system. Ministry of Shipbuilding Industry would develop gyroscope devices. Ministry of Machine Building would develop ground launching, refueling and transportation means. Ministry of Defense was responsible for conducting launches. Thanks to Dmitry Sergeyevich Mordasov, the main engineer, by July 1956 the draft was completed and the scientific tasks to be carried out by the satellite were defined. It included measuring the density of the atmosphere, its ion composition, corpuscular solar radiation, magnetic fields, cosmic rays, etc. Data valuable in creating future satellites was also to be collected. A ground observational complex was to be developed. That of the Sputnik 1 project dates back to December 17, 1954, when Sergei Korolev addressed Dmitry Ustinov, the Minister of Defense Industries, proposing the development of an Earth-orbiting, artificial, satellite, forwarding a report by Mikhail Tikhonravov with an overview of similar projects abroad. Tikhonravov emphasized that an artificial satellite is an inevitable stage in the development of rocket equipment in 1951, after which interplanetary communication would become possible. On July 29, 1955 the U.S. President Dwight D. Eisenhower announced, through his press secretary, that the United States would launch an artificial satellite during the International Geophysical Year, IGY. A week later, on August 8 the Presidium of the Central Committee of the CPSU approved the idea of creating an artificial satellite. On August 30 Vasily Ryabikov, the head of the State Commission on A-7 rocket test launches, held a meeting at the 5th Chirotam range, in Kazakh SSR, now at the Baikonur Cosmodrome. The satellite traveled at about 29,000 km per hour, 18,000 miles per hour. 8,100 meters per second, taking 96.2 minutes to complete each orbit. It transmitted on 20.005 and 40.002 MHz which were monitored by amateur radio operators throughout the world. The signals continued for 22 days until the transmitter batteries ran out on October 26, 1957. Sputnik 1 burned up on January 4, 1958. As it fell from orbit upon re-entering Earth's atmosphere, after traveling about 70 million km, 43.5 million miles, and spending 3 months in orbit.
Before the launch. Satellite construction project.
The history where Korolev presented calculation data for a spaceflight trajectory to the Moon. They decided to develop a 3-stage version of the A-7 rocket for satellite launches. On January 30, 1956 the Council of Ministers approved practical work on an artificial Earth-orbiting satellite. This satellite, named Object D, was planned to be completed in 1957-58. It would have a mass of 1,000 to 1,400 kilograms, 2,200 to 3,100 pounds, and would carry 200 to 300 kilograms, 440 to 660 pounds, of scientific instruments. The first test launch of Object D was scheduled for 1957. According to that decision, work on the satellite was to be divided between institutions as follows. USSR Academy of Sciences was responsible for the general scientific leadership and research instrument supply. Ministry of Defense